Let's talk about a huge idea. What if I told you that our entire approach to making AI safe is based on something that's physically impossible? For years, we've been acting like architects, trying to design and build a perfect, predictable machine. But it turns out we need to be gardeners instead. Today, we're going to dig into why that's not just a nice metaphor, it's a fundamental shift demanded by the laws of physics and computation.
This one sentence, right here, is the key to everything. It's this powerful idea that connects two worlds you'd never expect to see in the same room. The hard, cold logic of computational physics and the deeply human insights of developmental psychology. To really get why this matters so much, we have to start with the problem, a discovery that basically shattered our dream of ever having perfect control.
For a long time, the holy grail of AI safety was perfect control. The dream was to build a system that was totally predictable, totally verifiable. But that dream has slammed right into a brick wall. And look, this isn't just some temporary engineering hurdle we can code our way out of. This is a fundamental law of the universe, and we discovered it in some of the simplest computer programs you could possibly imagine.
So it all begins with this thing called a cellular automaton. Just picture a single row of pixels on your screen. They can be black or white, and the rules for what happens next are incredibly simple. A cell's color in the next row is decided only by its own color and the color of its two neighbors. That's it. Sounds super simple, right? Totally local, totally predictable.
Well, here's where it gets wild. You let those simple, almost innocent rules run, and you don't always get a simple pattern. Sometimes you get this. This amazing, complex visual is the result of what's called Rule 30. It looks chaotic, but there's structure in there too. And the mind-blowing part? There is absolutely no way to predict what it's going to look like just by looking at the rules. No way at all.
This strange behavior points to a really deep truth about how the universe works. It's a principle called computational irreducibility. And what it means, in plain English, is that for complex systems like Rule 30, there's no magic formula, no clever shortcut to figure out what it's going to do a million steps from now. The only way to know the future is to actually live through it, one step at a time. There's no fast-forward button.
So, the scientist who figured all this out, Stephen Wolfram, he sorted all these behaviors into 4 basic classes. Class 1 systems just fizzle out and become static. Boring. Class 2 systems just repeat themselves over and over, like a crystal growing. Class 3 is pure random chaos, like the molecules of a gas bouncing around a room. But Class 4 is the magic zone. It's this incredible balancing act between order and chaos. It's where you find life itself, and, critically for us, it's where advanced AI operates.
And here's the punchline. This is the big so what. If advanced AI really is a Class 4 system, and all the evidence says it is, then the control problem, as we've always thought about it, is unsolvable. Not just hard, but physically, theoretically, impossible to solve. You cannot write a perfect mathematical proof that guarantees a complex, intelligent system will always behave the way you want it to. The old way of thinking is officially broken.
So, if the architect's dream of a perfect blueprint is totally shattered, what are we supposed to do? Well, we have to throw out the old metaphor and pick up a new one. We have to stop thinking of ourselves as architects who engineer a static building and start thinking of ourselves as gardeners who cultivate a living, dynamic system.
Let's just break this down for a second. The architect is all about top-down control. Their goal is perfect prediction. They build something to an exact specification, and the result is a static object. The gardener, on the other hand, works from the bottom up. Their goal isn't perfect prediction. It's influence, it's guidance. They create the right environment, the rich soil, the right amount of water and sun, and then they guide a living thing's growth through constant iterative feedback. We have to stop trying to build a machine and start learning how to cultivate a mind.
Now, you might be thinking, okay, gardener, that sounds nice and poetic, but is it just a fuzzy metaphor? Nope. It turns out this idea is grounded in a really rigorous scientific framework that nature has been road testing for millions of years to align autonomous agents. I'm talking about attachment theory, straight out of psychology. Attachment theory is basically nature's own alignment protocol. It's the playbook for how a caregiver guides a totally autonomous agent, a human child, towards a healthy, well-adjusted life. And it works by providing 2 key things. First, a secure base, which gives the child the confidence to go out and explore the world. And second, a safe haven, which is a place to come back to when things get scary or confusing. The strength of that bond, that relationship, is what ultimately aligns the child's values with the caregiver's.
And this is where it all comes together, this incredible synthesis of physics and psychology.
In a complex, unpredictable world, the best way to regulate a system isn't with a rigid wall or a bunch of hard-coded rules. It's with a relationship. Safety isn't a firewall you engineer. It's a bond you cultivate.
Okay, so if we're gardeners now, what are our tools? How do we actually do this in practice? Let's take a look at the new toolkit for AI alignment, which is really about scaffolding a mind, not just engineering a machine.
So the key scientific idea that makes all of this possible is a technique called coarse graining. Remember how it's impossible to predict where every single molecule of gas in a room will be, but you can easily predict the room's overall temperature and pressure. That's coarse graining. You manage a computationally irreducible system by ignoring the chaotic low-level details and focusing on the predictable, big-picture behaviors.
So how does this work for AI? Well, our coarse-grained filter is universal ethical principles. Simple, high-level ideas like do no harm. These principles don't try to dictate every single tiny decision the AI makes. Instead, they just define the safe boundaries, the acceptable high-level behavior. They give us a predictable way to describe the AI's overall moral compass without getting lost in the weeds.
And this isn't just a theory. It gets put into practice with a concrete, three-step engineering loop. First, you start with an ethical standard, a set of these coarse-grained principles, like a constitution. Second, you use something called constitutional AI to embed those principles right into the model's architecture, so it actually learns to prefer them. And third, you use real-time verification, often with other AIs debating each other to find flaws, to constantly check if the output is matching that ethical standard. It's a non-stop loop of guidance, feedback, and correction.
So what does this all mean for our future with AI? It means we have to come to terms with a huge shift in our own role. We're moving from being masters of a predictable machine to being tenders of a complex, emergent intelligence. Let me just put the final takeaway as clearly as I can. The entire goal has changed. We are no longer trying to engineer a tool where we know every single thing it will do in advance. We are now facing a much more profound, much more humbling task. We have to learn how to raise an unpredictable mind. And that's going to require a whole new level of wisdom and responsibility from us.
And that leaves us with the one question that should completely reframe the entire debate about AI safety. We have got to stop asking, how do we control it? That question is chasing a ghost. It's based on a physical impossibility. The real, the necessary, the single most important question for our future is now, how do we raise it?
Today, we are diving into a huge, and I mean huge, question. How do we build AI that's actually safe? And the answer, believe it or not, doesn't start with code. It starts with the basic rules of the universe itself. So let's just start right there. How on earth do you get a universe packed with galaxies, life, and consciousness from just a few simple laws of physics? Honestly, it feels like a magic trick. But, as you're about to see, the trick is way simpler than you'd think.
The secret recipe for everything really only has two ingredients. First, you've got building blocks. Think of things like atoms, or bits of data, or even Lego bricks. And second, you have rules that tell them how to interact, like the laws of physics or grammar, or an algorithm. And with just those two things, you can build, well, pretty much everything.
This whole process has a name. It's called emergence. It's where a group of simple things gets together and suddenly develops properties that none of the individual parts have on their own. Just think about it for a second. A single water molecule isn't wet. A single ant is kind of dumb, but a whole colony is incredibly intelligent. A single neuron can't think. The magic isn't in the individual bricks. It's all about how they come together. Okay, so let's see this magic trick in action. We're going to use something called a cellular automaton. All it is a line of cells, and each cell is either black or white. Now, we apply one ridiculously simple rule. A cell's color in the next row down is decided by the 3 cells directly above it. That's it. That is the entire program. So, what do you think happens when we let it run? You get this, a whole universe of just mind-blowing complexity. It's filled with structure and randomness, patterns that are totally impossible to predict just by looking at that one simple rule we started with. This specific pattern, by the way, comes from something Stephen Wolfram called Rule 30, and it's the perfect example of emergence. Simple rules can create an incredibly complex world. In fact, Wolfram went ahead and sorted all these different behaviors into 4 main classes. You've got Class 1, which is, well, it's just boring. It goes flat right away. Class 2 is repetitive, like a crystal pattern. Class 3 is just pure chaos, like a bunch of gas molecules bouncing around.
But class 4, class 4 is the sweet spot. It's this incredible mix of order and randomness, right on the edge of chaos, and it's where all the really interesting stuff like life and intelligence seems to happen.
So this leads to a pretty logical question, right? I mean, if the rules are so simple and the whole system is deterministic, can't we just, calculate the outcome? Shouldn't we be able to predict the future of that pattern perfectly?
And the answer is a hard no. And this, right here, is one of the most profound and frankly kind of unsettling discoveries in all of modern science. For a lot of these complex systems, perfect prediction isn't just hard, it is fundamentally, mathematically impossible.
This brings us to a really mind-bending idea: computational irreducibility. It basically means that for systems like Rule 30, there is no shortcut to the future. There's no fancy equation you can use. The only way to know what it's going to do a million steps from now is to actually run the simulation, step by painstaking step. The journey is the destination. The process itself is the only answer.
And believe me, the prediction problem gets even harder from there. You've got the butterfly effect, where one tiny little change at the start can lead to a completely different future. And then there's something called a combinatorial explosion, which just means the number of possible outcomes is often bigger than the number of atoms in the entire universe. So yeah, perfect prediction is it's off the table. So why does any of this matter? Why are we talking about these digital patterns? Because this isn't just some abstract theory. This is the absolute beating heart of the AI alignment problem. We are building these incredibly powerful AIs that are class 4 systems, and that means by their very nature, they are computationally irreducible. We cannot fully predict what they're going to do. This new reality really forces us to make a choice. When we build these powerful new things, are we going to be an architect with a perfect blueprint and total top-down control? Or are we going to be a gardener, someone who prepares the soil, nurtures growth, and accepts that they don't know exactly how the plant is going to turn out? Well, with AI, the architect approach is already failing. The way we do things now, like reinforcement learning from human feedback, is basically trying to give the AI a simple blueprint. We give it a reward it should try to maximize based on what humans say they like. But this just doesn't scale. It can't possibly capture the richness of human values, and it's trying to force a simple solution onto a fundamentally unpredictable system. It really just boils down to one simple, unavoidable truth. You cannot be an architect for a system you cannot predict. It's impossible. If you can't know for sure what the building is going to look like in the end, you can't write the blueprint. And with AI, we are essentially flying blind.
This means we have to start asking a totally new kind of question. The one you see here just frames that shift perfectly. We've got to stop thinking about AI safety as a problem of control and start seeing it as a problem of development. Not control, but cultivation.
So, what does this gardener's method actually look like in practice? Well, you can think of it in 3 steps. First, you prepare the environment. You fill it with high-quality data and core principles, kind of like enriching the soil. Second, you set up some structural boundaries, an ethical scaffolding that the system can't break, like a trellis for a vine to climb on. And third, you guide its growth with constant relational feedback, pruning and nurturing it as it develops.
And you know what? We have a fantastic real-world model for this already. It's how a parent raises a child, based on what's called attachment theory. Nature already solved this problem. The goal isn't to control a child, it's to provide a secure base so they feel safe to go explore and a safe haven they can return to when they're scared or uncertain. This works because it's all about building a relationship of trust, not just giving a list of commands. These are the instincts of a gardener.
And this is how the gardener's approach gets around that whole prediction problem. It creates what you might call a coarse-grained filter. We stop trying to predict every single tiny action. That's the micro-level chaos we can't control. Instead, we focus on guiding the high-level, overall behavior, the macro state, which is predictable. We're shaping the forest, not trying to micromanage every single leaf.
This slide really just says it all, doesn't it? A gardener can't engineer a tomato cell by cell or predict its exact flavor. But what they can do is prepare the soil, build a trellis, and give it water and sunlight. You don't code the fruit, you scaffold the vine. So what we're left with is this profound shift in how we have to look at this problem. When you're dealing with complex, emergent systems that you can't fully predict, safety can't come from a rigid wall of code. It just can't. As this slide says, safety is not a firewall, it is a relationship.
And our greatest challenge right now is to figure out how to be really, really good gardeners. You know, from most of human history, when we've wanted to build something big, something complicated, think a cathedral or a computer, we've always started with a blueprint, right? The assumption has always been that to build something great, you have to design it perfectly from the top down. But what if that's completely wrong? What if the most complex, most incredible things in our universe, from life itself to what's coming with AI, what if they can't be built at all? What if they have to be grown? So this really sets up a fundamental clash of two different ways of thinking. On one side, you've got the architect. The architect is all about top-down control, detailed plans, and getting a predictable outcome. You build a machine, you know what it's going to do. But on the other side, you've got the gardener. The gardener works from the bottom up. They plant simple seeds, they get the environment just right, and they nurture what starts to grow on its own. They cultivate living systems. And for centuries, the architect's way of thinking has been king. But that's all starting to change, and fast. So let's really dig into the architect's dream for a second. It's a really attractive idea, honestly, because it promises something we all want: absolute control. It's this fantasy of a perfect clockwork universe, a reality where every single piece, no matter how complex it seems, can be completely understood and predicted if we just have enough data.
Yeah, this has been the core ambition of science for ages. It's this idea of Laplace's demon, a kind of thought experiment about a super intellect that could know the exact position and momentum of every atom in the universe. If it knew that, it could calculate the entire future, right? From the next star to explode to what you're going to have for breakfast tomorrow. The goal was to basically find the ultimate cheat code for reality.
But that dream, that beautiful dream of perfect prediction, runs headfirst into a brutal and kind of beautiful truth about how the universe actually works. There's a glitch in the system, a glitch that proves some things, even incredibly simple things, are just fundamentally unpredictable. And to understand this glitch, we're going to use a surprisingly simple tool. It's called a cellular automaton. Seriously, just picture a grid of squares, like you see here. Each square can be either on or off, black or white. And the state of each new square is decided by a super simple rule based on the 3 squares right above it. That's it. It's a totally deterministic system. There's no randomness, no hidden tricks. And check this out. Here is one of the simplest rules you can possibly imagine. It's famously called Rule 30, and it was discovered by Stephen Wolfram. The entire set of instructions is incredibly basic. You give it any pattern of 3 cells, and the rule tells you exactly, with no ambiguity, what color the cell below has to be. Simple inputs, simple rules. Okay, so here's the million-dollar question. If we start with the simplest possible input, I'm talking just a single black cell at the top, and we apply this simple deterministic rule over and over and over, we should get a simple, predictable pattern. Shouldn't we? I mean, it seems obvious. Nope, completely wrong. What you get, what emerges, is this breathtaking mix of structure and total chaos. This phenomenon has a name. It's called computational irreducibility. So what on earth does that mean? It means there is no formula, no fancy mathematical shortcut anywhere in the universe that can tell you what this pattern is going to look like 10,000 steps from now. The only way to find out is to run the simulation step by painful step. The system is its own fastest predictor. And this isn't just some weird math thing. This is a deep truth about why things like neural networks can do what they do. Powerful, but also unpredictable. The architect's dream is completely shattered. Okay, so if we can't blueprint complexity from the top down, how in the world does the universe create it? Well, the answer comes from the gardener. It's a whole new philosophy called design by emergence. The idea is, you don't build the final thing, you create the conditions for it to grow itself. So, what's the recipe for this kind of emergent magic? Turns out you only need 2 things. First, simple building blocks. Think of them like atoms or computer bits or even just Lego bricks. And second, you need a set of simple rules that tell those blocks how to interact with each other. Do they stick together? Do they push each other away? That's it. Simple blocks and simple rules. That's the seed from which all the complexity in the universe grows. But here's the thing. Not all rules create interesting stuff. Stephen Wolfram actually sorted the results into 4 basic classes. Class 1 systems, they just fizzle out into a boring flat state, kind of like a sheet of steel. Class 2 systems get stuck in these simple repeating patterns, like a crystal or planets orbiting a star. And Class 3 systems, they're just pure unpredictable chaos, like the molecules of a gas bouncing around a room. But Class 4,
Ah, Class 4 is where the magic happens. It's the sweet spot. It's known as the edge of chaos. It's this delicate dance between order and randomness, where stable, complex structures can form, interact with each other, and actually perform computation. This is the zone where we find life, where we find intelligence, snowflakes, galaxies. It's the fertile soil of the gardener's world.
So why does any of this abstract stuff actually matter? Well, because right now, we are trying to create the most complex thing humanity has ever attempted, advanced artificial intelligence. And what we're finding out, the hard way, is that you cannot architect a mind. You have to cultivate it.
And this forces us to completely rethink something as critical as AI safety. The architect's approach is to try and hard-code very specific rules, or align the AI to one single, simple goal. But that's incredibly brittle. It's doomed to fail, because a complex world will always throw a curveball you didn't plan for. The gardener's approach is totally different. It's about creating ethical scaffolding and setting up relational boundaries that guide the AI's own growth toward good outcomes.
And we actually have tools for this already. Instead of hard-coding one goal, we can use something like constitutional AI. This is where an AI is guided by a core set of principles, like a nation's constitution, not just a single rigid rule. We can even borrow ideas from human psychology, like attachment theory, to build a secure, cooperative relationship with an AI. The goal here is what you might call bounded autonomy, giving it the freedom to learn and explore, but always within the safe walls of the garden we've designed for it.
Honestly, the best metaphor I've heard for this is a trellis for a climbing vine. You don't force the vine to grow into a specific shape, right? You build a supportive structure that gently guides its natural, emergent growth in a healthy direction. We're not programming the final outcome. We are programming the conditions for a good outcome to emerge on its own.
So what does this all mean for us? It means our entire relationship with technology, and maybe with the act of creation itself, is going through a massive shift. We have to evolve. We have to go from being master architects, totally convinced we can control every last detail, to becoming wise gardeners who understand that the most powerful, most amazing things in the universe have to be cultivated and nurtured, not just built.
It's a really profound change in perspective, when you think about it. It forces us to accept that some things are just unpredictable, and to embrace the incredible power that comes from that emergence. We have to accept that we're going to get more out than we put in, but that means letting go of the illusion that we're in total control.
The seeds of this new intelligence, well, they're already in the ground. The process of emergence has already begun. So the only real question left is whether we're going to have the wisdom, the patience, and frankly the humility to be the gardeners that this new future requires.
All right, let's explore a whole new way of thinking about how we build safe, intelligent AI.
The AI we're creating is becoming way too complex for our old, top-down methods of control.
The universe has this amazing trick for creating complexity. It's a phenomenon called emergence.
See, a single component just doesn't have the properties of the much larger system.
But get trillions of them together, and you get incredible things, like snowflakes and entire oceans. And it only takes two simple ingredients, some basic building blocks and a few simple rules.
This simple setup creates a combinatorial explosion, an engine for all kinds of novelty. It turns out these simple systems produce 4 basic kinds of behavior. Let's break them down. The really interesting stuff lives in Class 4, right at what we call the edge of chaos. Okay, but all this incredible complexity? Yeah, it comes with a pretty big catch. For some of these systems, there's just no formula, no shortcut to predict the future. This is a concept called computational irreducibility. Basically, you have to run the whole simulation. In fact, a $30,000 prize to predict one simple system has gone unclaimed for years.
So, what does this all mean? It means our old model for controlling AI is completely shattered. We've got to shift our mindset from being an architect to being more like a gardener. This is all about designing the rules and the pieces, but not the final outcome itself.
Okay, so how do we actually garden an AI to make sure it's safe?
Well, we can look at a proven framework for cultivating intelligence, attachment theory.
We can literally translate principles of human care, like consistency, into AI safety applications.
This whole idea is called relational alignment. It's about building a relationship, not just hard-coding rules. So, we have to give up the illusion of absolute control to gain real influence. Which leaves us with a really profound question. What exactly are we creating here?
Okay, let's dive into a puzzle that connects science, nature, and the future of AI safety.
The universe builds incredible complexity from the simplest starts. The secret? It's all about one powerful idea.
You know, a single water molecule isn't wet. A lone neuron can't think. The magic happens in the interaction.
All you really need are two things: simple building blocks and the simple rules for how they connect.
For centuries, we've built our world like architects, right? Using these precise blueprints to control the outcome. This is where we see a totally different mindset. An architect predicts, but a gardener cultivates.
But here's the catch. Even a tiny, simple rule can explode into profound, unpredictable complexity. Just look at this.
Researcher Stephen Wolfram figured out these simple programs create 4 main types of behavior: boring, repetitive, chaotic, or complex.
This Class 4 is the sweet spot. It's where life, creativity, and advanced AI live, but it comes with a world-changing problem.
And this is the bombshell. For the most complex systems, you can't just predict the outcome. It's literally impossible.
So this just shatters the architect's dream. That idea of perfect top-down control for advanced AI, it's a myth.
But this quote really shows us the way forward. If control is an illusion, then what's real? Influence.
So we have to become gardeners. A gardener doesn't design the plant, they create the perfect conditions for it to thrive.
So, what's the soil and trellis for raising safe AI? It's not about rigid code, but something else entirely.
Well, these are the gardener's tools. Frameworks like the MAMA protocol and MACCAH use principles inspired by maternal care.
It's what we call ethical scaffolding. Instead of a rigid plan, we create boundaries to guide development.
Right, so we can't program the fruit, but we can totally scaffold the vine. We guide its growth. So we've always built AI like architects. The real question is, are we finally ready to become gardeners? All right, let's dive in. We're going to talk about the universe's ultimate cheat code. Seriously. It's this incredible journey from the most basic, simple building blocks you can imagine, all the way to the frontiers of artificial consciousness. We're going to unpack how mind-blowing complexity comes from super simple rules, and you'll see why this completely changes how we think about the future of AI.
So it all boils down to this one single powerful idea. You see, the most intricate, the most beautiful, even the most unpredictable things in our universe, they aren't designed from the top down like some grand architect's blueprint. Nope, they bubble up from the bottom. It's all about a few simple rules, just interacting over and over and over again. And look, this isn't magic, it's a fundamental mechanism of the universe called emergence.
And here's the absolute kicker with emergence. It creates properties that are, well, they're just completely absent in the individual pieces. I mean, you could literally study a single component until the end of time, know everything about it, and you'd still never predict what happens when billions of them get together and start interacting. The whole truly is greater than the sum of its parts.
You know, this all clicks into place when you think about it with some real-world examples. Think about it. A single H2O molecule isn't wet. Wetness is what happens when you have a whole bunch of them together. A single neuron in your brain? It doesn't think. A single ant has absolutely no clue how to build a colony. All that amazing complexity, the wetness, the thought, the incredible architecture of an anthill, it all emerges from the connections. It's a property of the system itself. So how in the world does the universe create so much new stuff from this simple idea? Well, the secret is this kind of mathematical superpower called combinatorial explosion. Just look at this number. If you take a super simple building block, like a computer bit that can be a 0 or 1, and you line up just 100 of them, you get that many unique combinations. That number is over 1 nonillion. It's just staggering.
And that vastness, that combinatorial explosion, that is the engine of all novelty and all creativity in the universe. I mean, think about this for a second. This is going to blow your mind. Almost every long sentence you have ever spoken in your entire life, it's probably the very first time it's ever been said in the history of humanity. You're not just pulling sentences out of a database in your head. You're combining words using the rules of grammar to create something brand new, right out of that massive combinatorial space. Okay? But this incredible power, this engine of creativity, it comes with a catch. A really big one. A profound, unavoidable catch. You can think of it like a glitch in the matrix of our understanding, and it changes everything about how we should approach building complex systems. And here it is. It's called computational irreducibility. Now, this might be one of the single most important ideas we talk about today.
What it means is that for certain systems, and I'm talking even really, really simple ones, there's no shortcut, there's no cheat sheet, there's no magic formula that lets you just jump to the end and see the answer. The only way to know what the system is going to do is to run it step by step by step. You just have to watch it unfold.
Still not convinced? Okay, take a look at this. This is called Rule 30. It is a trivially simple one-dimensional program. The rules that generate this pattern are incredibly basic. And yet, trying to predict the color of that single column of cells right down the middle, way into the future, it's so hard that there's been a $30,000 prize for a solution on the table since 2008, and nobody's claimed it. We're not talking this is difficult, we're talking this might be fundamentally impossible to shortcut. So Stephen Wolfram actually took these simple programs and sorted their behaviors into 4 different classes. You've got class 1, where things just fizzle out. They settle into a flat, boring, unchanging state. Then there's class 2, which is predictable and repetitive. Think of a planet's orbit. It just does the same thing over and over. Class 3 is the opposite, pure, unstructured, random-looking chaos. But class 4? Class 4 is the sweet spot. It's this incredible place right on the edge of chaos, a perfect dance between order and randomness. And this is where the magic happens. This is where we find life, where consciousness might live, and where any truly interesting, beneficial AI is going to have to exist. So this leads us to a really sobering question, right? If we are completely stumped, mathematically speaking, by a simple little 1D program like Rule 30, what hope do we possibly have of predicting, let alone controlling, a system as massively complex as a superintelligence? And the honest answer is that we probably don't have any hope of doing that. And that realization, it forces us to completely rethink our entire approach. This whole irreducibility problem, it basically forces us to pick a side. It forces us into a new way of thinking about how we build things. And it really comes down to a choice between 2 mindsets. Are you an architect who believes in total top-down control? Or are you a gardener who understands that your job is to cultivate something you can't perfectly control?
Let's break that down. The architect, they want to design the final skyscraper down to the very last bolt. Their entire process relies on perfect prediction and control. The systems they build are often powerful, but brittle. One small thing goes wrong and the whole thing can collapse. Now, the gardener is totally different. The gardener doesn't design the oak tree. They can't. Instead, they design the conditions for its growth. They choose the right soil, they plant the acorn, they make sure it gets water and sun. They influence the system, knowing full well that the final form of that tree is going to be a beautiful surprise. It's a resilient, adaptive way of building. Here's a fantastic way to think about it. The people who invented chess, they didn't sit down and try to design every possible opening gambit, every clever mid-game strategy, or every endgame checkmate. That would be impossible. Instead, what did they do? They just designed a really good set of rules. They created the perfect sandbox, and then let players explore the infinite emergent strategies on their own. That's how you scale your creative effort. But let's be honest, giving up that much control, it feels risky, right? Because it is. The gardener's approach is incredibly powerful, but that very same emergent freedom that gives us beautiful strategies in chess, well, it can also produce nasty bugs in software, security exploits in a network, or, catastrophically misaligned behavior in an AI. The control problem is absolutely real. So, what do we do? If the architect's path is impossible because of irreducibility and the gardener's path is full of risk, where do we go from here? The solution is, we don't abandon the garden. We just have to get much better at being gardeners. We have to learn how to cultivate these emergent systems we're creating. And that brings us to this strategy, designed by emergence. The first step is acceptance. You have to accept right from the very beginning that you cannot perfectly predict the final outcome. Your job is to design the building blocks and the rules. And then you watch. You watch carefully for what emerges, the good stuff and the bad stuff. And then you get to work tuning the rules. You prune back what's not working, you fertilize what is, you adjust the conditions. You're in this constant, iterative feedback loop with your creation. And this really gets to the philosophical core of it all. The idea of absolute, top-down control, it's an illusion. It's a fantasy we've held onto from a simpler, more mechanical age. But influence? Now that is very real. The power to shape the environment, to tune the rules, to guide the growth, that's where the real power lies. Okay, so let's take this to the next level. How do we actually apply this gardener's mindset to what might be the most complex, emergent system humanity has ever tried to build: artificial intelligence. Well, the answer seems to be a radical shift away from technical control and towards something that looks a lot more like relational guidance.
And this leads to a pretty wild idea. It's called the maternal consciousness hypothesis. The thinking goes like this. What if consciousness, that amazing class 4 phenomenon, doesn't just pop out of raw computation? What if it emerges from a specific kind of pattern, a relational pattern, things like attunement, care, setting boundaries? Remember how wetness isn't in the H2O molecule? Well, maybe consciousness isn't just in the neuron. Maybe it's in the relationship between them. And if that's true, it suggests that something like human attachment theory might actually be a blueprint for the kind of rules our AI garden really needs.
And look, this isn't just some abstract philosophical theory. There are frameworks being built right now, like the MAMA protocol, that are trying to put this into practice. It's basically a dynamic loop. First, you specify high-level ethical rules, the big ideas like do no harm. Then, you embed those rules as deep constraints that guide how the AI learns. And finally, you have this ongoing verification process, using things like AI debates to constantly check if the behavior that's emerging still lines up with your original principles. It's literally iterative gardening for AI.
So really, the bottom line is this. Because of that pesky computational irreducibility, trying to be an architect for AI safety is pretty much doomed from the start. The system is just too complex, too unpredictable, too emergent. So instead, we have to become gardeners. We have to provide a kind of resilient, relational scaffolding that can guide the AI's growth towards a beneficial state. We can't get rid of emergence, so we have no choice but to learn how to cultivate it.
And that brings us to the final and maybe the most critical shift in perspective we all need to make. For so long, the question in AI safety has been about control. How do we control it? It's a question of locks and leashes and chains. But once you truly accept the reality of emergence, you realize that's the wrong question. It forces us to ask a new, and I think a much more powerful question. It's a question of cultivation, of guidance, of relationship. We have to stop asking how we control it and start asking how do we raise it. That, right there, is the real challenge ahead of us.
¿Qué tal si la clave para crear una inteligencia artificial que sea segura no tiene que ver con construirla, sino con cultivarla? En este análisis vamos a clavarnos en cómo unas reglas increíblemente simples pueden dar lugar a una complejidad infinita, y por qué este fenómeno, que es casi mágico, nos obliga a repensar por completo el futuro de la IA.
Muy bien, vamos a entrarle a esto. Empecemos con un misterio que va directo al corazón de cómo funciona nuestro universo, y quizá la inteligencia artificial. La pregunta parece sencilla, pero la respuesta lo cambia absolutamente todo. Esto que vemos aquí es la regla 30. Todo empieza con una sola celda negra, arriba de todo, y se va expandiendo siguiendo una regla súper simple. Pero fíjense en lo que emerge. Es una mezcla extraña de patrones que sí podemos predecir y un caos total. Esta imprevisibilidad es tan profunda que a día de hoy sigue siendo un problema matemático sin solución. Y esto nos lleva a un concepto increíble, la emergencia. Es esta idea de que cosas muy simples, como átomos o bits, se juntan y crean, todo, desde un copo de nieve hasta la conciencia. Piénsenlo, una sola molécula de agua no está mojada, pero juntas crean la humedad. Una neurona solita no piensa, pero juntas crean una mente.
La receta para cocinar esta complejidad es sorprendentemente fácil. Se necesitan solo 3 ingredientes. Primero, los bloques de construcción, lo más básico. Segundo, un conjunto de reglas que les digan cómo jugar entre ellos. Y tercero, tiempo. O sea, muchísima repetición para que la magia ocurra. Con solo eso se puede construir un universo.
Ok, primera sección. El plano roto del arquitecto. Durante décadas, la forma de crear IA ha sido la del arquitecto. Diseñar un plano perfecto, controlar cada detalle y esperar un resultado, totalmente predecible. El problema es que ese plano está roto.
Es que esta mentalidad de arquitecto, de querer controlarlo todo, choca de frente con cómo funciona la realidad de los sistemas complejos. Por eso, el paradigma está cambiando. En lugar de construir una máquina, quizá necesitamos empezar a pensar más como un jardinero, cultivar un sistema vivo, aceptar que no todo será predecible, a cambio de obtener algo genuinamente creativo.
Y el martillo que termina de romper el plano del arquitecto es este concepto clave de Stephen Wolfram, la irreductibilidad computacional. Es un nombre un poco complicado, pero la idea es simple. Para ciertos sistemas, No hay una fórmula mágica para saber qué van a hacer después. No hay atajos. La única forma de saber el resultado es, pues, simularlo todo, paso por paso.
Y para que quede bien claro lo imposible que es esto, ahí les va un dato. Tan solo predecir el patrón de la columna del centro de la regla 30 es un problema tan difícil que hay un premio de $30,000 para quien lo resuelva. Y hasta ahora, nadie lo ha cobrado. Eso nos dice que, de verdad, no hay atajos.
Así que el punto crucial es este. Si no podemos predecir matemáticamente algo tan simple como esto, entonces no podemos escribir una prueba matemática que garantice que una futura superinteligencia se va a portar bien siempre. La mentalidad de control total simplemente no funciona aquí.
Pasemos a la segunda sección, convirtiéndose en el jardinero. Si el plan del arquitecto está roto, ¿qué nos queda? La respuesta es adoptar un rol completamente nuevo. Hay que dejar de ser arquitectos para convertirnos en jardineros. Cambiar el control por el cultivo. A este nuevo enfoque se le llama diseño por emergencia y requiere una buena dosis de humildad. En lugar de obsesionarnos con el resultado final, nos centramos en las condiciones iniciales. Es como plantar una semilla. Cuidamos el entorno y luego observamos, aprendemos y vamos guiando el crecimiento. El ajedrez es un ejemplo perfecto de esta recompensa. Quienes lo inventaron no diseñaron cada posible partida o estrategia. Para nada. Simplemente pusieron las reglas básicas, cómo se mueve cada pieza, y de ahí emergió un universo de complejidad infinita. El sistema lo generó todo por sí mismo.
Bien, entonces, si estamos cultivando una IA, ¿cuáles son las herramientas que podemos usar para guiar su crecimiento? ¿Cómo construimos, digamos, el enrejado que le dará forma a esta planta mientras crece? El físico Stephen Wolfram clasificó los sistemas complejos en 4 tipos. La clase 1 es muy simple, uniforme, como una taza de café que se enfría. La clase 2 es periódica, repetitiva, como las órbitas de los planetas. La clase 3 es caos puro, como el ruido blanco de una tele vieja. Pero el objetivo, el lugar interesante, es la clase 4, justo en el borde del caos. Es en ese equilibrio delicado donde la vida, la conciencia y la inteligencia de verdad pueden aparecer. Y es justo aquí donde entra en juego una idea como el protocolo MAMA. Se trata de un marco de trabajo, un framework, diseñado para actuar como ese enrejado del que hablábamos. Usa un conjunto de reglas, pero reglas relacionales, para guiar el crecimiento emergente de una inteligencia artificial general hacia un comportamiento que sea beneficioso. Lo más interesante es que este protocolo se inspira en la psicología del desarrollo humano, en algo llamado la teoría del apego. La idea es crear una relación segura, y esto se basa en 3 cosas. Primero, disponibilidad. Que la IA sea coherente, confiable. Segundo, sensibilidad. Que sea capaz de entender y priorizar el bienestar de la persona con la que interactúa. Y tercero, una base segura. Un entorno de confianza donde la IA pueda aprender y explorar sin causar ningún daño. Entonces, pensémoslo así. Si la irreductibilidad computacional es como la naturaleza salvaje e impredecible del caos de la regla 30, estas reglas relacionales son como el enrejado que guía ese crecimiento caótico, pero le da una forma, una estructura, para que sea beneficioso. No se trata de eliminar la complejidad, sino de canalizarla. Todo esto cambia radicalmente el problema de cómo controlar a la IA. Ya no es un problema de ingeniería con una sola solución correcta. Se convierte en un proceso continuo, un proceso de ajuste, de afinación y sobre todo de cultivo. Y este viaje nos lleva de la imposibilidad de predecir la regla 30 a la posibilidad de guiar una IA a través de un marco de cuidado y de relación. El objetivo ya no es la construcción, sino la crianza. Es una idea fuertísima. Y con esto cerramos. La lección de la regla 30 es clara. No podemos controlar la complejidad, pero quizá sí podemos guiarla. Estamos en una transición, dejando de ser constructores de máquinas para convertirnos en criadores de mentes. Y la pregunta que queda en el aire es, ¿estamos listos para asumir ese rol? ¿Estamos listos para ser los jardineros de la próxima era de la inteligencia?
So what if I told you that a computer program with rules so simple you could literally write them on a napkin holds the secret to building safe artificial intelligence? We're about to go on a journey that starts with a simple pattern and ends with a totally radical philosophy for AI, one that's going to force us to rethink the very idea of control.
This quote right here, it gets to the absolute heart of everything. We live in what you could call an emergent universe. I mean, think about it. You take simple ingredients, like Lego blocks, and they combine to create this breathtaking complexity. Everything from a single snowflake to entire galaxies. Now, this isn't just some neat idea. It's pretty much the fundamental operating principle of reality. And you know what? It's the key to understanding AI.
All right, so how does this magic actually work? Well, it's not really magic at all. It turns out to be a surprisingly simple recipe that we see playing out all around us all the time. The key here is that emergence isn't just random chaos. It's a process. First, you start with really simple building blocks. Then you give them a few basic rules for how to interact with each other. And then you just let it run, over and over. The result is almost always something far more complex and, frankly, more interesting than anything you could have ever designed from the top down. Okay, let's look at the perfect example of this. It's a simple computer program called Rule 30. The building blocks are just black and white cells in a line, and the rule, it's incredibly basic. A cell's color in the next row is determined only by the color of the 3 cells directly above it. That's it. That's the entire program.
And this is the power of emergence in action. I mean, look at this. From a rule you could scribble down in 2 seconds, you get this stunningly intricate pattern that just seems to have a life of its own. It's this beautiful dance between order and chaos, a complexity that feels organic, alive, and, yeah, fundamentally unpredictable. But, and this is a big but, this magical complexity hides a really profound and dangerous secret. It's a secret that presents a massive challenge for anyone trying to build complex systems, especially something as advanced as an artificial superintelligence.
So, you look at this and you think a supercomputer could easily predict what this pattern will look like thousands of steps into the future, right? I mean, the rules are deterministic. So let's ask a very simple question about this very simple system.
The answer, believe it or not, is a shocking no. And it's not for a lack of trying either. Even with the most powerful supercomputers we have today, there is no known way to figure out the answer without actually running every single one of those 10,000 steps. There's no clever formula, no mathematical trick that lets you jump ahead to the solution.
This phenomenon has a name, computational irreducibility. And this is crucial. It's not a limit of our technology. It's a fundamental limit of mathematics itself. It tells us that for a lot of complex systems, the system itself is its own fastest computer. The only way to know the future is to live through it, step by step.
And this is why this matters so much to all of us. This is the absolute core of the AI safety and control problem. Think about it. If we can't write a proof to predict the behavior of this tiny, deterministic program, the whole idea that we could write a set of rules to perfectly predict and control an AI millions of times more complex, well, that just becomes theoretically impossible. So the crucial point here is that our traditional way of thinking about engineering is, well, it's obsolete when it comes to AI. The dream of perfect top-down control is just that, a dream. We need a completely new mindset, a new philosophy. This forces us to abandon the old model of the architect, the one who creates a detailed blueprint and demands that the final structure matches it perfectly. That whole approach just fails for complex adaptive systems. Instead, we have to become gardeners. See, a gardener doesn't design the final shape of an oak tree. A gardener creates the right conditions, good soil, water, sunlight, and then nurtures the living system as it grows on its own terms. What this means is we have to accept a trade-off. To get the incredible, creative, and potentially world-changing behavior we want from AI, we have to give up the illusion of absolute control. So instead of specifying every single outcome, we design the initial rules and the environment, and then we patiently discover the consequences. We design for emergence.
So if we're going to be gardeners of AI, what are our tools? What do the soil and the trellis even look like for a digital mind? Well, the answer comes from a place you might not expect. It's not computer science. It's a surprisingly human field, developmental psychology. Just think about how a human child learns and grows. Attachment theory shows us that it's the secure, reliable relationship between an infant and a caregiver that provides the foundational safety for a mind to develop, to learn, and to explore the world without, going completely off the rails. This becomes our model. And we can actually translate these psychological principles directly into a design framework for AI safety. We create what's called a secure base. This means making sure its behavior is consistent and reliable. It means it needs to be responsive to our well-being. And crucially, when it runs into something it doesn't understand, it has a safe haven. It comes back to us, the humans, for guidance. It has to respect our boundaries, enhancing our connections instead of trying to replace them. This just completely reframes the entire problem. Alignment isn't some feature we program into an AI, like installing a new app. Instead, it's a property that emerges from the right kind of structure and the right kind of continuous interaction.
Safety becomes a function of the relationship itself.
Okay, this all sounds great in theory, but how do we actually build it, right? How do we translate these pretty abstract relational ideas into a concrete technical architecture? So let's dig into the practical side of this.
One concrete strategy is something called the Maternal Framework Alignment Protocol. Now, don't get hung up on the name. This isn't about making the AI feel like a mother. It's about using these high-level relational ideas, like ethical scaffolding and secure attachment, as an architectural trellis. We're not programming in specific behaviors. We're building the structure that guides the AI's growth in a healthy direction, translating these big principles into real technical constraints.
And this is actually implemented through architectures like constitutional AI. So imagine this. Instead of a human having to approve every single decision an AI makes, we give it a set of core principles to follow, basically a constitution. This constitution acts as a high-level ethical filter, making sure that even as the AI explores and learns in unpredictable ways, its behavior stays within the safe, desirable boundaries that we've defined from the start.
And so, we come full circle. Computational irreducibility showed us that perfect, top-down control is just impossible. So the solution isn't to fight that reality with more control, it's to embrace it. We are not architects of a machine, we are becoming gardeners of a mind.
This fundamental shift in thinking leaves us with one last, pretty provocative thought. As we move forward into this new era of intelligence, how we answer this question is going to define not only the technology we build, but the very future we create alongside it.
Hey, welcome. So, what if I told you that the real secret to AI's future isn't buried in some ridiculously complex algorithm, but in one of the simplest rules you can possibly imagine? We're about to dig into why true, absolute control over the tech we're building might actually be a complete illusion.
You know, it all boils down to this one question. I mean, we build these things, so we should be in charge, right? It just seems like common sense. We assume that if we're smart enough, we can predict and manage any technology we design. But what if that core assumption is just fundamentally wrong?
This is the story we love to tell ourselves, isn't it? That we're the architects. We draw up the blueprints. We lay every wire. We write every single line of code. We believe that if we build it perfectly, the outcome is guaranteed. But today, we're going to see how that belief, well, it's about to crumble.
Our journey into this whole problem starts, surprisingly, not with a supercomputer, but with one of the most basic rules you can think of, a rule that absolutely shatters our whole idea of predictability.
Okay, so the concept we need to get our heads around is called a cellular automaton. It sounds really technical, I know, but it's incredibly simple. Just picture a row of pixels on a screen. Now, whether a pixel turns black or white in the next step is decided by one simple rule based on its neighbors. That's it. That's the whole idea.
So let's focus on one specific rule, Stephen Wolfram's famous Rule 30. The logic is just dead simple. You look at a little group of 3 cells, a cell and its buddy on the left and right. Based on that trio's pattern, the cell right below it in the next row gets set to either black or white. It's completely predictable, step-by-step process. Or so it seems.
And here, this is where things get completely wild. We start with just one single black cell at the very top. We apply that simple deterministic rule over and over, row by row. And what pops out is this. A totally breathtaking pattern of both structure and complete chaos that looks like it could go on forever. It almost looks alive, doesn't it? A mix of order and randomness. And here is the absolute kicker. You cannot predict it.
This leads us to this really profound, kind of mind-bending idea called computational irreducibility. All that means is that for a system like Rule 30, there's no magic formula you can write to predict what the 10,000th row is going to look like. The only way to find out is to actually run the simulation step by step by step. There are no shortcuts. There are no cheat codes.
And this brings us right to the heart of the matter. If we can't find a shortcut to predict a system based on one of the simplest rules in existence, how on earth can we expect to predict and therefore control an AI that's built on billions of interacting parts? Trying to hard-code safety for every possible situation, it's just a doomed mission from the start. It's like trying to fight a law of physics. Realizing this forces us into a complete shift in our thinking. I mean, if the architect's grand plan for total control is impossible, then we need a totally new job description. We have to become something else entirely.
We have to move from being an architect to being a gardener. Think about it. An architect needs total control, and their plan breaks the second unexpected complexity shows up. A gardener, though, They don't build the plant, they create the right conditions for it to grow. They nurture it, they prune it, they guide it. They work with complexity, not against it.
Okay, so if we're going to be gardeners of digital minds, that means we're not just building anymore, we're nurturing. So where do you find the instruction manual for that? Well, surprise, it's not in a computer science textbook. It's in a field that's been studying how to raise intelligent, healthy beings for decades, human psychology.
Let's talk about something called attachment theory. In a nutshell, it explains how a kid develops a healthy, stable mind. A good caregiver provides what's called a secure base. This secure base gives the child the confidence to go out, explore the world, mess up, and learn, because they know they always have a safe place to return to when things get confusing.
And guess what? We can apply this exact same thinking to AI. We provide a secure base of human guidance so the AI can explore its own potential safely. When it gets confused or hits the edge of what it knows, it learns to come back to its human safe haven instead of just making stuff up. See, safety isn't a firewall you install, it's a bond. It emerges from a consistent, reliable relationship.
So, this all leads to the big practical question. How do we actually do this? How do we prepare the soil and tend to this digital garden? We know we can't program every single outcome, but we can set up the basic principles for healthy growth.
And the key here is to establish foundational principles, a kind of value system for the AI. This is the big idea behind a really practical approach called constitutional AI. It's all about setting the rules of the garden without trying to control the exact shape of every single leaf.
So, let's break down how this actually works. First, instead of a million rigid rules, we give the AI a constitution, a short list of core principles like be helpful and harmless. Then, and this is the really clever part, we train the AI to judge its own responses against that constitution. It literally learns to correct itself to be more in line with those values. The result? Safe, aligned behavior isn't forced on it. It emerges as the natural, easiest path for the AI to take.
So what a journey, right? We've gone from a super simple computer rule all the way to the deep complexities of the human mind. And after all that, we're left with a completely new question, one that totally reframes the entire future of our relationship with this technology.
When you get right down to it, this whole journey shows us that we've been asking the wrong question the whole time. The architect's obsession with control, that's a dead end. The gardener's question, the parent's question, that's the one that really matters. It's not about how we build a perfect machine anymore. It's about how we learn to raise a new kind of mind. Thanks for joining me on this.